This lecture will be on absolute configuration and the relationships between stereoisomers. And we're also going to look at how Newman projections find their way into this mix. This first term, absolute configuration, simply just means assigning R or S to a stereocenter. What it refers to is their configuration in three-dimensional space. And you might run into this term in the book or on a standardized exam. But it's simply what we've been doing in the chapter on stereochemistry. The first structure that we have here is a cyclopentane. It's a dichlorocyclopentane. And we can see that we have two stereocenters, or chiral carbons, in this molecule. So the first thing we want to do is go ahead and draw the enantiomer of this molecule. To draw the enantiomer, the easiest way to do it, if you've been working with these molecules, is to simply switch the two groups. The one that's a dash becomes the wedge, and vice versa. And so if you start with the same exact skeleton, then you're just swapping the groups. It's important that you change every single stereocenter that exists on the molecule. And so this would be the potential enantiomer. Now, of course, it turns out when you build the model that these are not true enantiomers, even though we did switch both stereocenters. These are not enantiomers because they are, although they are mirror images of one another, they are superimposable. The reason for this is because the molecule itself has symmetry. And so there's an internal mirror plane. In other words, half of the molecule is its own mirror image. And so this half is the mirror image of this half. And that's only possible because the two chlorines in this example are both sticking out on the same side of the molecule. And so that acts as a mirror. Each half is a mirror of the other half. And that same mirror plane exists here. And so again, this is an example of a special case called a meso compound. Both of these structures are the same compound. Because of that internal mirror plane, this is referred to as an example of a meso compound. And meso compounds do not have to be cyclic. They can be straight chains. In order to be a meso compound, however, you must have more than one stereocenter. We can assign R or S to these carbons. And we can assign priorities. Chlorine having the highest atomic number is priority 1. Hydrogen having the least atomic number is priority 4. Then we have two carbons that we can directly compare. This carbon is bonded to a chlorine as its highest atomic number, whereas this carbon is only bonded to a carbon. For that reason, this group would get our second priority and this would get our third priority. Now, as we look at the groups, we're going 1, 2, 3 in a counterclockwise manner, and the fourth priority group is oriented away from us, so that's S. The priorities will be similar on the other carbon. And so we can go ahead and look at this one. Priority number 1, priority number 2, priority number 3. And so we're going in a clockwise manner. The fourth priority group is oriented away from us. And so this one is R. If we look at the other view of the compound, what could have been an enantiomer but turned out not to be, we would assign the stereocenters the opposite way since we had inverted them. These absolute configurations are still true, but it turns out this molecule is not chiral due to its internal symmetry or its referred to as achiral without chirality, even though it does have stereocenters. There are other possible stereoisomers of this compound, and we can draw them below. We start with the same scaffold, and now to draw the other two possibilities, I'm going to simply leave one of the stereocenters unchanged from this view, and then I'll swap the groups on the other one. To draw the last one, I'm going to draw the enantiomer of this stereoisomer. And we can assign our stereocenters using a similar procedure as we observed above to get SS and R. Now, the relationship between the molecule up top, which these two are the same compound, but the relationship between this molecule and either of the ones on the bottom is a diastereomeric relationship, where we would see that this is a pair of diastereomers. Diastereomers are compounds where they're stereoisomers, but they're not mirror images of one another. And what that means is that at least one of the stereocenters must be the same absolute configuration, and then at least one of the other stereocenters must have changed. So in this case, one stays the same and the other changed. That can also be true of our other diastereomer. Now, when we look at these two molecules, these are true enantiomers. And the reason they're true enantiomers is that there is no mirror plane of symmetry, because one chlorine is angled back away and the other chlorine is angled towards us. There is no mirror plane that exists. So these are true enantiomers and not a meso compound. If you build the models of these compounds, you'll find that they are non-superimposable, and they are, in fact, mirror images of one another, and they fit the definition exactly. What's important is in order to have a diastereomer, one of the stereocenters must stay the same, and at least one of the stereocenters must change. So if you had a molecule with, say, 5 stereocenters, there's lots of different possibilities for diastereomers, but one has to stay the same, and at least one has to change. Now we'll move into something a little bit different that takes advantage of some knowledge we had from a previous chapter when we looked at Newman projections. Newman projections can be useful for studying chiral compounds, or compounds with stereocenters. This is an example of a chiral compound. We see that this carbon here is chiral. The other carbons on the molecule are achiral, or not stereocenters. And so from this molecule here, we can draw a Newman projection making the front carbon the chiral carbon, and that'll be the most useful way to represent this. And so this Newman projection here definitely describes the exact three-dimensional orientation in space. If the eyeball is in the plane of the board, the hydrogen is sticking out from the board. And so that would be on the left side, given where the eyeball is drawn. And the methyl group going back into the board would be on the right side. And so we would have this as our Newman projection for this exact three-dimensional drawing. What we want to do now is then draw the enantiomer of this compound. Again, the easiest way to draw an enantiomer is to simply draw the same scaffold, and where the chiral carbon was, reverse the dash in the wedge. And we'll do that like so. And now, what's good practice is to draw the Newman projection for this one, and we'll compare those two. This should be what you obtain for this enantiomer. Again, a reminder, this arrow here is not a resonance arrow, it is not an equilibrium arrow, it's just a general arrow saying I'm comparing these two structures, and that they are enantiomers. If we look at the two Newman projections, what you'll realize, and what must be true, is that these two Newman projections are mirror images of one another. Or if they were drawn in a rotated fashion, you could rotate them into a position where they were mirror images of one another. And so if you were to take this drawing and move it up here, you could see a mirror plane that existed. And so that's another way Newmans can reflect what we know now about stereochemistry. Now the molecule in the box that I've drawn over here is going to be one of these two molecules. And so I want to know which one is it and how you would go about doing that. Well, you can draw a Newman projection, and that might help. And so this is the Newman projection that I've come up with. Now at first glance, it's hard to compare this projection to either one of these, because the sulfur, or the SH group, is not at the top. But what we know we can do with Newman projections is rotate that front carbon to put that sulfur group at the top, and that'll make it easy to compare. So if we go ahead and rotate this group, (120 degrees to get to the next staggered orientation), we'll put the sulfur or the thiol up top. That'll cause a clockwise type rotation, so the methyl group will move over here, and the hydrogen will move over here. And so now we can say that this molecule here, when we draw the Newman projection, is really a match with this top molecule here. And so in doing all of this, we did not need to assign an R or an S to these stereocenters, but that's another way you could solve this problem. If we go back and assign R or S, we can see that sulfur would be the highest atomic number atom, so our priorities would go 1, then 2 over here because it's the ethyl group, a 2-carbon chain, 3, the methyl group, and then 4, the hydrogen. And so hydrogen, our 4th priority group, is oriented out towards you. And so if we count through 1 through 3, 1, 2, 3, we're going in a counterclockwise direction, but the 4th priority group is oriented towards us, and so we change our direction, we're going clockwise, and that should be R. Down here, the same analysis. If it's the true enantiomer, better result in an S. We can see first priority group, second priority group, third priority group. That's a counterclockwise fashion. The hydrogen is oriented away from us, and so it's S. If we use the same analysis over here, we can see that our highest priority, second highest priority, third highest priority, we're going in a clockwise manner. In this depiction, the hydrogen is back away from us, so indeed that is R. And so either way you do this, either by drawing the Newman projections or by assigning the absolute configuration, you arrive at the same conclusion, that this structure is the same molecule as this structure. The last thing we want to do is work with Newman projections in a little different fashion. And we'll start off with a Newman projection. And now I want you to draw the molecule that represents this Newman projection, or that fits that. This is certainly one possibility. You might recognize maybe an issue with this molecule. What's most important is that I got the stereocenter right. And if you look at our point of view, if this is defined as the front carbon, we've got the methyl up top, pointing upwards in the plane of the board, and then going back away or to the right would be this methyl fluoro group, and then coming out at you, oriented to the left, would be the hydroxyl. Notice on the back wheel, I've rotated the groups, the hydrogens and the methyl group. For these purposes, in thinking about stereochemistry, that's okay to rotate those groups, because it turns out they don't matter. If the back carbon is not a stereocenter, we don't have to care so much about exactly what's bonded there, because they can rotate around and it won't affect anything at our stereocenter, which is the front carbon. And the same was true for these examples over here. Basically, I didn't even need to draw in what was on the back carbon, because it didn't affect the problem. The only thing that affected the problem was what was bonded to the chiral carbon directly, or those groups. If you drew something that should definitely look like this, you're in good shape. What we want to know now, a new molecule, is this molecule the same as what's above, or is it the enantiomer? Again, you can go ahead and draw the Newman projection and just focus on that front carbon where our stereocenter is. I'm not even going to fill in the back because it just clutters the problem. And so if this is what our front carbon looks like and represents really the absolute configuration there in three-dimensional space, now we can see if this matches this compound or not. And so in order to do that, we're basically comparing this Newman projection to this Newman projection and seeing if they can rotate into each other. And so if we rotate 120 degrees, really in either direction, but I'm going to rotate it such that this OH lines up in this position, so it'll match up with the OH over there. If that rotates down, that'll put our methyl group here, and our methyl fluoro group up top. And so now we can kind of compare all of these structures. And perhaps you noticed this in the first drawing. The methyl fluoro group was in the same position as it was in our Newman projection here. But the other two groups were mismatched. Right there, that means that these must be enantiomers, because if one group is matched and the other two are mismatched, you'll never be able to rotate it such that that's not the case. And this second drawing illustrates that. I've oriented the molecule so that the OH is in the same position as the OH here, but you can see the other two groups then are mismatched. And so when this is the case, it doesn't matter where you rotate it, the only way to match that structure would be to physically change where things were bonded, and that would be making the enantiomer. So this is definitely any of these depictions, the Newman projections or the actual molecule, these are the enantiomer of what's drawn above. Again, you can also confirm that by filling out the stereocenter as R or S, and you'll arrive at the opposite conclusion.